Hi kids, ready to start looking at finding extrema for 3D. So first just going to pop up kind of like the boring definition, right? If we are in some region around a point and the function values all around it are all greater or equal to that point, we say we have a relative minimum. Local is a synonym for relative, and then the same for maximums, right? All maximums and minimums are local. Some local are also global. The synonym for global is absolute. But remember, we have to have, in order to be able to tell whether we are absolutely the highest or lowest, we have to have some area that we can, in a bounded area that we can test to see, right? So in Calc 1, if you remember, I taught you how to identify a list of critical points of a function and then zero in on those suspects to see if they were indeed turning points in your function, right? And if you remember, you had to look at the first derivative where the slope of the tangent was equal to 0. So you either had a horizontal line or you had where your derivative does not exist. So you were looking for places like where you had, a turning point like this. So your first derivative was equal to 0. You had a min, you had a max. But you could also have the first derivative not exist and have a turning point. First derivative not exist and have a turning point. But you could also have a horizontal tangent where you did not have a turning point. Or you could have a derivative not exist and not have a turning point. In multivariable, we are going to define a critical point or stationary point of a function in terms of x, y, if the partials are equal to 0, right? So the rate of change with respect to x, the rate of change with respect to y, right, is 0 in both, right? So they're both equal to 0. That is an and statement. Or if either partial does not exist, either or both. So very similar, right? First derivative has to be equal to 0. It's just that I have to have the first derivatives, plural, be equal to 0 or not exist. So let's try an example here. And we are only going to be looking for critical points. We're not talking about maxes and mins yet. So step 1, find the partial of x, right? And these ones are not bad to do. Partial y. Check to see, are there any places where they do not exist? Nope. So now set them equal to 0, solve the system because you need points that make both derivatives equal to 0 with the same point. So I'm just going to do a little bit of algebra 1 here. Subtract 3x squared, divide by -3. Plug in x squared for the y. So x is equal to 0 or x is equal to 1. So in my list of suspects, my critical points is when x is equal to 0. Whoops. And x is equal to 1, how do I find y? Well, when x is equal to 1, y is y squared, y is x squared. When x is equal to 0, y is equal to 0 squared, right? Done and done. That's all they wanted, was a list of critical points. Gave it to them. Now let's suppose that I want to, from my list of suspects, I want to go further. I want to take them to court. And I want to find out if the suspects are turning points on my 3D surface. So we are going to use the second derivative test for extrema, but the multivariable version of it. All right, now if you remember first derivative, in Calc 1, when you had a horizontal tangent and the second derivative was positive, you were concave up, you thought maximum. When the first derivative was equal to 0 and the second derivative was negative, you were concave down and you thought minimum. If the second derivative was equal to 0 and the first derivative was equal to 0, we usually ended up with our poi situation, right? So we're going to, bam. Oh my gosh, you weren't expecting that now, were you? I call this the second partials test. So we have this big D here. And before you, don't let yourself look at this right now, but this big D is going to be equal to a number. If that big D is positive, then you need to look at your second derivatives. And just like Calc 1, if your second derivative is positive, then you think horizontal tangent, concave up, relative minimum. If that big D is positive, then you look at your second derivative and you say, oh, my second derivative is negative. Then you think horizontal tangent, concave down, relative maximum. It's like this partials test, this big D partials test thing has to go along with the first derivatives being equal to 0 before you can move on. So your first derivative is zeros and big D is positive. Then you look at the second derivatives, the actual second derivatives. And by the way, if you really wanted to look at the FYYs instead of the FXXs, you could, doesn't matter. I'm going to skip 3 for a minute and I'm going to go to 4. Just like this case in Calc 1, when the first derivative was equal to 0 and the second derivative was equal to 0, the second derivative test for extrema was inconclusive and we went back to the first derivative test. But we often ended up with a poi at that situation. Here, if your first derivatives are equal to 0, but capital D is also equal to 0, this is our inconclusive case. And there's nothing to go back to. So don't worry about this. Why would I test you on this, right? If I don't have another test to send you to. This inconclusiveness is actual inconclusiveness, and that's what we have computers for. However, we do have a scenario now in 2D that we did not run across in our Calc 1. In 3D. Something called a saddle point. That only occurs if your first derivatives are equal to 0, your partials are equal to 0, and this big capital D, the second partials, is negative. If your second partials is negative, then you don't even go to the second derivatives, right? You don't even need to. You automatically know you have a saddle point. Don't quite know what a saddle point is yet, but let's just say it's poi-ish. All right, so let's practice one. So we're going to start with this surface, and we're going to start off exactly the same as we did before. Right? Here's our partial x. For partial y. Set them equal to 0. Going to try to solve them simultaneously. So I'm going to look at the first one, pull a 6x out. When x is equal to 0 or y is equal to 1, that makes the first equation equal to 0. So I'm going to take each one of these and put it into the second equation and see at that x what y's create the second equation to be 0. So when I plug in 0 for x, this goes away, and I end up with 3y squared minus 6y is equal to 0. So I end up with y is equal to 0 or y is equal to 2. So over here for my list of suspects, I have when x is 0, y is 0, and when x is 0, y is equal to 2. But I still have to check when y is equal to 1. So when y is equal to 1, 3x squared is still 3x squared, plus 3 minus 6 is equal to 0. That's 3x squared minus 3. So add 3 to both sides. So when y is 1, x was either positive 1 or negative 1. So I have a list of 4 suspects. Now I'm going to need this information to go on. Now I didn't explain that big capital D formula, not yet. Did that, check. Now, just so I have it, I'm going to put our list of suspects over here. That's the critical points. I need both first derivatives. And then I need to do the second derivatives. So what's my second derivative here? Second derivative with respect to x. Second derivative here with respect to y. Oh, looky, they're the same. Now, though, I have to go back here and take the second derivative with respect to y. Here's that fancy formula, and I just like it written like this a little bit better, right? You're going to take your second derivative with respect to x, multiply it times the second derivative with respect to y, and subtract the second derivative of x with respect to y, and you're going to square it. This is a determinant of the vectors made up of right? And if you think about that, right, when you do a second order determinant, take the product of the main diagonal, subtract the product of the minor diagonal, and that's what you have here. So there I go. Second derivative with respect to x, second derivative with respect to y, second derivative of x with respect to y. And I'm just going to plug in each one of my points and see if I get a positive second partials. If I get a positive second partials, then I need to go to either step 5 or step 6 and plug in my suspects. All right, so let's try. Suspect 1, plug in 0, 0. Second partials is greater than 0. So then check the second derivative at the point 0, 0, and you get -6. Therefore, you have this situation, and 0, 0 is a local max. 2, plug in 0, 2. So I have no x, I'm just plugging in 2 here. So I get 6, still 0 squared. I get 36, which is greater than 0, so the second partials is greater than 0. Now go to the second derivative. Go to the second derivative, plug in 0, 2. And I get +6. So I have the horizontal tangent concave up situation. 0, 2 is a local min. Now I'm going to plug in third suspect, 1, 1. When I plug in 1, I get 0, 0. So my second partials, my big D is less than 0. I do not need to go to the second derivative. I go directly to, therefore, the point 1, 1 is a saddle point. Last one, -1, 1. Still, since y value is still 1, I still get a 0 and a 0 here. 6 times -1 is -6, but -6 squared is still 36. Minus 36 still gives me a -36, which means my second partials is negative. I don't need to go to the second derivative. So -1, 1 is also a saddle point. Okay, so again, this video, I didn't really do much with the drawings or looking at anything like I did with the first video, but we'll do more of that for this topic in our class, where I'll show you what these graphs look like and what the heck is a saddle point, right? But I want you to think about what a saddle point might be, where you have your derivatives, your second derivatives, both of them are equal to 0, but it's not a turning point. What could that mean on a 3D surface? We'll talk about that in our next live session.